Good morning, everyone. In the previous class, we have discussed the variable voltage characteristics and the control of induction motor through stator voltage. From today's class onwards, we will see the control of induction motor through the stator frequency. So by varying the supply frequency or stator frequency, how the speed or the torque of induction motor can be controlled, that we will see from today class onwards. Okay, before going to the main concept, we will discuss a few points about the introduction and the importance of frequency in the control of speed or torque. Generally, the speed of AC machine, either synchronous machine or induction machine, AC machine is related to the stator, we can call as a supply also, supply frequency. Therefore, the supply frequency of the drive is varied or is changed if the speed of the machine is to be changed. So the speed of the induction machine can be controlled with the change in the supply frequency or stator frequency, because we know, this is directly proportional. The synchronous speed Ns is directly proportional to the frequency. Ns is the synchronous speed in RPM, which is directly proportional, not equal to, it is directly proportional to the stator frequency. This relation we know because we know the equation for synchronous speed in the AC machine, which is Ns is equal to 120 into F by P, where F is the frequency and P is the number of poles. We know this formula. 120 is constant, P is the number of poles for a specified or a particular designed machine. Number of poles is also constant. So 120 by P is a constant value. That means from this relation, we can say that the synchronous speed is directly proportional to the stator frequency or supply frequency. And we can change this frequency with any of the converter. Like we have cycloconverters, we have voltage source inverters, we have current source inverters and PWM inverters. Using any of these systems, we can change we can control the frequency of the system, frequency of the induction motor. But in order to get the good torque capability and avoid the saturation at low frequency, the stator voltage is also controlled to maintain the constant flux. So stator voltage will also be varied with respect to the frequency under low frequency conditions, because this is to avoid the saturation. The saturation will be happened due to the flux. So to maintain this flux constant, stator voltage is also be varied to maintain the flux constant or to avoid the saturation problem and also to get the good torque capability. We will see this point later in this class, because this is the major point in the frequency operation or the frequency control. We will see detailedly about this point with the equations. We will discuss this point again in the later class. And also the motor speed is varied up to the base speed based on this voltage control. And in order to regulate or in order to increase the speed above the base speed, then the voltage must kept constant. Then the stator frequency is varied to the above its rated value, above or below. It depends upon the speed. So up to the base speed, we need to vary the voltage and frequency in order to maintain the flux constant. After the base speed, we need to keep the stator voltage constant and we need to alter the stator frequency or supply frequency above or below the rated speed. Sorry, rated frequency value. Sorry, rated value, right? Therefore, the cost of the converter and the complexity of the control system both are much high when compared with the DC drives. Because of the converter size and the complexity of the control mechanism, this is not much used in many applications, because which is complex and costlier compared with the DC drives. So DC drives are preferred over induction motor control with the stator frequency. But many of the efforts are being made to make this stator frequency control more reliable and more economical. So this is the major disadvantage because of the system complexity and cost. The stator frequency control have limited applications. In order to increase the number of applications, many of the efforts are being made to make this stator frequency control of induction motor economical as well as reliable, right? And coming to the variable frequency characteristics. So in order to get the variable frequency characteristics, we need to see the equation 6.1, which is very important. Just now we have discussed that the synchronous speed is equal to 120 F by E, where 120 is a constant value, P is the number of poles, and F is the stator frequency or the supply frequency. Right. So from equation 6.1, we can say that the stator frequency is one of the speed control of three-phase induction motor, where the synchronous speed is directly proportional to the supply frequency. Right. The synchronous speed is directly proportional to the supply frequency, because 120 is a constant, number of poles is also a constant, then NS is directly proportional to F. So the synchronous speed of the motor and the motor speed can be controlled above or below the base speed by varying this supply frequency. See, if we change the speed, change the frequency, then automatically the speed of the machine will also be altered. Okay. And the supply voltage of the induction motor can be written as V is equal to 4.44 into phi. Phi is the flux, F is the stator frequency, T is the number of turns of the stator winding, T is the number of turns of the stator winding, and K is the constant value. So this equation we know, and I have given this equation in the examination also in the paper. So 4.44 into flux into frequency of the stator or the supply frequency into the number of turns, stator winding turns, into the constant. So this is the induction motor voltage equation. From this voltage equation, the flux, which is also called as air gap flux, can also be written as like this. See, the flux value, bring all these terms this side except this flux. Now we can write the flux is equal to V by F into 1 by 4.44 into K1 into T. 4.44 is a constant, K1 is a constant, T is the number of turns for a particular or for a designed machine, T is also constant value. So that means this entire term is constant value. So from this equation 6.3, we can say that the air gap flux phi is directly proportional to V by F, the ratio of voltage to the frequency. So V by F must be varied in order to control this flux, particularly for low frequencies. See, from this equation, we can say the flux is inversely proportional to frequency. That means if the frequency value is very low, that means if the denominator is very low value, then flux is very high. If a flux is very high, then machine will saturate. Because of the high magnetic flux, the machine will goes to saturation. then the machine performance will completely degraded because of uneven currents, uneven torque production, and uneven production of AC voltage on the windings will distort the complete performance of the induction motor. So in order to keep this flux constant, or in order to bring the flux below the saturation point, we have to control the stator voltage up to some extent for this low frequency values. This is very much important. Okay. And the K is a constant value, and this K can be written as frequency, which is the original frequency, or also called as operating frequency of the machine. And F rated is the base frequency. Generally, in India, we will take this rated frequency or the base frequency as 50 hertz. So the F is the rated frequency or the base frequency. F rated means F means operating frequency, which is the actual frequency that is applying to the machine. So K is a constant per unit value of frequency. Okay. And next, here we have two different conditions. We have two different conditions in order to plot the variable frequency characteristics. The first condition is the operation of induction motor below the base speed, which is also called as at constant V by F ratio. Below the base speed or constant V by F ratio. Or we can also call as constant flux, which is K less than 1. We know the K is F by F rated. If the actual frequency, F rated is, let us say F rated is 50 hertz. F rated is 50 hertz. If the base or the actual frequency or the operating frequency is 50 hertz, then K value will be 1. 50 by 50, we will get 1. Okay. K less than 1, that means the actual frequency or the operating frequency of the machine must be less than the rated value, which means the frequency must be less than the 50 hertz, then we will get K less than 1 condition. So this is first operating condition. When the frequency is low, in the introduction part, I have discussed this point also. For lower frequencies, the voltage is maintained or the voltage is varied in order to keep the flux constant. From equation, this flux is directly proportional to V by F. If the actual frequency is low, which means K less than 1, then this flux value will be very high. If this flux value is high, means the machine will get saturated. So under saturation condition, the machine performance is very poor. So in order to avoid those problems, we need to keep this flux as constant by changing the stator frequency, which is V. So first operation describes the same thing, which is the motor operating below the base speed or at a constant V by F ratio, or simply V by F is also called as flux, so at constant flux. So the K value is less than 1. So this is the torque equation. Actually, this torque equation, maximum torque equation, we have derived the maximum torque equation in 511, but the 511 equation is in speed and stator voltage. But this equation 6.4 shows here the maximum torque equation in V by F form in terms of frequency, the slip and all other parameters have been replaced, and also here XS and XR dash will be there, but XS and XR both are reactive parameters, where XS can also be written as a 2 pi F LS. Here frequency term is there, so instead of XS here 2 pi F LS has been written here. Similarly, XR dash value also 2 pi F into LR dash. So instead of XR dash, this value is written, and the squaring of 2 will give 4 pi, will be pi square. So L plus LR dash whole square. So all the terms have been replaced with the frequency terms, because here we are controlling the speed as well as the torque of the induction motor with the help of supply frequency or stator frequency. Okay, so the maximum torque equation, which we have seen in equation 5.14 in the previous part of the third unit, that has been changed here because we have completely modified that equation in terms of frequency, because we need to control the frequency here. So that thing we have done here. So this equation 6.4 gives the maximum torque for frequency control. And we have seen that the flux is directly proportional to V by F. So from that equation, if there is any reduction in the supply frequency, that means if the operating frequency is going down the rated frequency, which is 50 hertz. If the operating frequency is going down the 50 hertz value, then the terminal voltage has to be increased, so that in order to maintain the flux constant. If the frequency is changing, we need to keep this flux as constant value. So flux must be kept constant, which is V by F. So if the frequency is decreasing, excuse me, so this voltage has to be decreased. So the ratio between voltage and the frequency, which is V by F ratio, will maintain constant, so that the produced flux will also be constant. This is the main motto for this condition, for this operating condition. Because for this operating condition, we need to maintain the flux constant. Otherwise, if the flux is saturated, if the flux is more for the less frequency, then the motor performance will be degraded. So in order to avoid that condition, we need to vary the supply frequency also. It is mandatory to vary the supply frequency so that the flux will be maintained constant, will not be saturated. So the induction motors are designed to operate at the knee point of the magnetization characteristic to make the full use of the magnetic material, which means the flux. And therefore, the increase in the flux will saturate the rotor, which means this will increase the magnetizing current, which also distorted the line current and voltages that is presented in the induction motor. Not only that, it will also increase the core losses, copper losses, stator copper losses, and also produce acoustic noise also. And if the flux is increased beyond its rated value, then because of the saturation, the torque capability of the motor will also get degraded, which means completely the performance of the induction motor will completely degraded. Hence, the variable frequency control below the rated frequency, which means below the 50 hertz. If the 50 hertz is our rated value, then below the 50 hertz, generally for this condition, this condition can be carried out to maintain this air gap flux constant with the help of stator voltage. If the frequency is 25 hertz, which means it is decreased half of the times, then the stator voltage is also decreased half of the times, so that the frequency is decreased half of the times and the stator voltage is decreased half of the times. Resultant, the flux will be constant. Okay, using this formula, the flux will be maintained constant for this operating condition, which means K less than 1 condition. Okay. And for the simplification, I have chosen that the ratio of RS by F, the value of RS by F is very much less than, because the stator resistance is very much low. The stator resistance is very much low in terms of 0.1, 0.2 ohm. So this RS by F value is very much low compared with this term. Simply 2 pi into Ls plus Lr dash. So when compared with this term, RS by F is very much low, so that I am going to neglect this RS by F terms. So the resultant torque, maximum torque equation will become K1 into V by F whole square by, here we have this term becomes 0, then here root and square will get cancelled. 4 can be written as 2, and pi square and root can be cancelled. So 2 pi into Ls plus Lr dash. So this is the maximum torque condition when the flux is constant, or when the K value is below 1. Okay, so from equation 5 says that with a constant V by F ratio, if this V by F ratio is constant, the motor develops a constant maximum torque, because see, K1 is a constant value, Ls, Lr dash both are constants. If we maintain V by F ratio is also a constant value, then the torque production is also a constant. So we can produce a constant torque under this condition. Therefore, the motor operates in constant torque mode when it is required that the same maximum torque is retained or achievable at lower speeds also. So see here, this torque, maximum torque equation is independent of speed here. There is no speed equation here. So for lower speeds also, means irrespective of speeds, we can achieve the maximum torque condition under this operating mode, because under this operating mode we are keeping this V by F ratio as constant. Other all parameters are constant, right? So that means the maximum torque, the developed maximum torque must be constant for any different speeds. For load speeds also we can achieve the maximum torque. So we need not to bother about the speeds. And you can observe here two symbols are shown, plus symbol and minus symbol. We know the plus symbol indicates for the motoring action and minus symbol indicates for the braking or regenerating action. Okay, if the torque, the produced torque is minus, then the motor is operating under braking or regeneration. If the torque is plus, then it is operating under motoring condition. We know that one. So plus and minus, that depends upon the motoring action or regenerative action. Okay. So in order to maintain or in order to get the constant torque under different speed conditions, definitely we need to operate the motor under constant V by F ratio. Right? So the speed torque characteristics can be constant, which means that for different speeds, the torque is a constant value for a period of time, because we are getting the maximum torque for different speeds. But if the frequency is increasing, then automatically the torque will also get increased, because this frequency is in denominator. So if denominator, this frequency will be in the numerator, and if it is increasing, then the torque will also increases. The speed will also increases. Let's see this speed torque characteristics in the next figure, the next slide. So you can observe here, this is the speed torque characteristic curve, and this is the relation between V and F of V and F relation, and it means voltage and frequency relation. Now you can see here different speed. All these are the different speed torque characteristics. You can see for the same speed, you can observe this negative side represents the generating action and positive side represents the motoring action. Okay, torque in the negative side means generating or braking action. Torque in the positive side means motoring action. You can see the torque speed characteristics which are constant. You can see here, and the switching frequency, the supply frequency or the stator frequency is increasing, then the speed will also increase like this. So after the base speed, you can see the speed still increases after the base frequency. That means at this point, this is the maximum or the synchronous speed. After the synchronous speed, we need to further increase the frequency so that the speed will also get increased, because speed and frequency both are directly proportional. Okay, right. And we will discuss the second operating mode as well as the complete detailed torque speed characteristics in the afternoon class.